Let's see. It's 300 slides. I think I have split it into, I have a clear distinction, when I would break.
I think we should get started because we have a lot to cover. Today, Konstantinos is going to present virtual memory. It may take longer than 3 hours.
No.
Let's see. Yeah, because he has a lot of material. Konstantinos is a senior PhD student working with me in Safari. He's going to graduate next year. And this is his baby, virtual memory. So he's done a lot of work on virtual memory. And he's going to cover some basics as well as some recent research on the topic. And you already have an assignment, a bonus assignment, based on the simulator he and his colleagues developed together, which they had a tutorial on. It's also his birthday today, so maybe we can wish him happy birthday to begin with. That's the beauty of being in academia. You get to present on your birthday. And, and he wants to go to academia, so he's getting used to it. All right, go ahead, Konstantinos.
Thanks, Onur, for the introduction. Hi, everyone. I'm Konstantinos, as Onur said. So we're going to talk about virtual memory today. It's my favorite topic, as Onur said. So first, I would suggest that you take a read at this nice write-up from Onur, the intelligent architectures for intelligent computing systems. I think Onur gives a very nice overview of the research being done in the group about this sort of intelligence architectures approach, where he argues for data-centric, data-aware, and data-driven architectures. So I'm going to make this basically virtual memory-centric, virtual memory-aware right now. These are the required readings. I would suggest that you take a look at these papers and books, part of this book. And let's dive directly into the basics. So how do programmers right now interact with memory? Using loads and stores, right? When I want to write to memory and when I want to load from memory, there is a specific interface that I do this with. So what would be an ideal memory? An ideal memory would have a zero access time, which means no latency, infinite capacity. I would assume that memory is infinite. It would have zero cost. I wouldn't pay anything for it, and infinite bandwidth. I go to it and fetch data with no penalties. What's the abstraction right now that we have in most modern systems? We have virtual versus physical memory. So the programmer, when you write C programs, when you write Python programs, you do not see physical memory. You see virtual memory. This lets you make the assumption that memory is infinite. You don't need to care about the physical backing storage that data is stored in, right? You only care about expressing your virtual addresses. In reality, though, physical memory size is much smaller than what the programmer assumes, and the system magically, this magic I will explain today, somehow maps virtual addresses to the physical memory. So this is done automatically, transparently from the programmer. The programmer doesn't need to care about how this is done, basically. So a small physical memory can appear huge to the programmer and makes the life much, much easier. And this is one of the most important benefits, key benefits that virtual memory brings to the game. However, we have a mapping, right? We let the programmer write virtual addresses, but at the end of the day, these need to be resolved in physical ones. And this indirection and this complex system software and architecture makes the life of the architect and the designer a bit harder. And this is the classic example of the programmer microarchitect trade-off. I will give you a real life example, which I came up yesterday with. So this is a warehouse, right? And in a warehouse, you can imagine you have a huge warehouse that stores thousands of items. So when you have a worker that wants to access an item, the worker doesn't know the physical location of the item in his memory, right? What he knows is he has simply a barcode of the item. And then the barcode, when you match it with some physical location through the inventory database, that's when you can go to the physical location and access this item. So this sort of warehouse abstraction resembles the computer's virtual memory subsystem. So why do we need virtual memory? So virtual memory brings the benefits of automatic memory management. So the programmer does not need to deal with physical addresses. Each process has its own virtual address space, and there is an independent mapping between virtual to physical addresses. When you write your program and you express virtual addresses, there is isolation between your program and your colleague's program because you express in virtual addresses, and then the operating system is responsible for dealing with this isolation. This enables code and data to be located anywhere in physical memory. You can express your virtual address, you allocate an array, but this can map anywhere inside the physical memory. This isolates code and data of different processes in physical memory. There is a guarantee from the modern systems that when you express virtual addresses, you will have isolation between different processes. And third, you can share code and data between multiple processes. For example, the computing system might say, oh, colleague A and B want to map these same virtual addresses to the same physical page because they want to share the data, right? That's something that they will need to do manually if there was no support for virtual memory. So this is an example of a system. Let's take a step back and say, okay, let's say that we don't have virtual memory and our system only can access memory using physical addresses directly. And this is how most early supercomputers were working with, like early personal computers, many older embedded systems. So imagine the CPU here, which generates only physical addresses, right? So what is a problem? What are some problems with this approach? First, physical memory is of limited size. What if you need more? Let's say you wrote your program, right, to use 20 kilobytes of physical memory, but the available memory is 10 kilobytes. Then what do you need to do? You need to rewrite your program every time the physical memory changes. So should the programmer be concerned about the size of the code and data, whether it fits the physical memory? For example, if some of the data need to be moved to the disk because you cannot fit it in the physical memory, does the programmer need to explicitly state which one of the data is going to be placed in the disk and which one is going to be placed in the physical memory? Second, we have multiple programs that may need the physical memory. Can anyone think of what would be the problem if we had tenants in the same system that would write using physical addresses? Only physical addresses. Anyone? So the problem basically would be that you would need to coordinate with each other about the physical locations that you are going to use. Basically, if you have a single physical byte storage, then you would all need to have a consensus that, okay, programmer A is going to use this part of the physical memory. Programmer B is going to use another part of the physical memory. And how can you make sure that someone is not malicious and it's going to overwrite or read the data of another user in the system? Another problem is that you have ISAs that have a much larger address space compared to the physical memory size. For example, you might have a 64-bit address space with byte addressability, while your memory does not match, of course, the size of 16 exabytes, right? So you need a way to map these 64-bit addresses to some physical memory addresses. So these are the difficulties basically of direct physical addressing. The programmer needs to manage physical memory space. It's difficult to support code and data relocation. It's difficult to support multiple processes and isolation. And it's difficult to support data and code sharing across processes. So let's see right now how does virtual memory work. So the idea is that we will give to each program the illusion of a very large address space while having a small physical memory. Basically, the programmer doesn't care what is in the system. The programmer only sees a very large virtual address space. The programmer does not worry at all about managing the physical memory in this context. So the hardware and the software somehow magically and cooperatively manage the physical memory space to provide this illusion that we have isolation for each independent process. And the problem here in virtual memory is the indirection and the mapping of the addresses. So when an address gets generated by an instruction to the program, this is a virtual address. It is not the physical address, which is used to address the main memory. When you write your C and Python programs and you print the addresses, right? These are virtual addresses. These are not physical addresses. Underneath, the system goes and translates these addresses so that it's able to access the physical memory. So an address translation mechanism maps the virtual addresses to the physical ones. And there are many different ways of implementing this. It could be done solely in hardware. It could be done with hardware and software working closely. It could be done only at the software level. This is an example. We have two applications. So for example, in your personal computers, right, there are multiple applications running. So we have two applications, application 1 and application 2. And these applications operate on different pieces of data, right? The green ones and the yellow ones. And we can see here that application 1's data has been placed in the second and the third position in the physical memory, while application 2's data has been placed in the fourth and the sixth position in the physical memory. So this is basically this indirection. This is the mapping. The first address of virtual address space 1 from the application 1 maps to the second page in the physical address space. The second address maps to the third space in the physical address space. However, this can change. In another system, you may not have the same exact mapping, right? So somehow we need to store this mapping. We need to find out how can we resolve this indirection between the virtual and the physical address space. Another key benefit employed by this approach is the heterogeneity in the physical data storage. What does this mean? So we have virtual addresses, right? And some of it contain legit data, for example, the blue regions here. Some of this data, the first and the fourth page, can translate to physical addresses that reside in the main memory, in the physical memory. However, if, for example, our main memory is fully occupied, we can store some other addresses, the other blue ones, the bottom blue ones, to the hard disk. So what benefit do we get here? We have transparent support for multiple different physical data storage, which means that the programmer doesn't need to care whether data is stored in the main memory or hard disk. They just need to care, the operating system or the system as a whole needs to make sure that this data is mapped to the corresponding device. In most modern systems, most access is hit in the physical memory, and that's what we want, right? Because this, as Onur and you have seen in most of the lectures here, we want the data to hit in memory. We want to find the data. It's best if we find them in the caches, of course, but we need to find them in the main memory because the disk accesses are very expensive. But if the memory is full, then the programmer doesn't need to be concerned. The operating system and the system as a whole is going to move your data to the hard disk to make sure that you can run your program. So most modern systems use the physical memory basically as a cache. So the physical memory is a cache for pages stored on the disk, and you can think of it as a fully associative cache, which means that the virtual page can be potentially mapped to any free physical frame. So there are similar caching issues which we have covered earlier, like placement. How do you place, like where and how to place and find a page in the cache? How do you replace? How do you make room in this memory in the cache to fill it up with pages? What's the granularity of the management? Do we use large pages, small pages, uniform pages? What's the write policy? Do we write back? Do we have write through? Again, let's map it back to the warehouse example. In the warehouse, you have virtual addresses which correspond to barcodes. So workers identify each item purely by scanning the barcode. So they do not know where it's stored. They don't care basically where it's stored. And barcodes provide a clean, unified namespace. You can think of it as a label, basically. So this is exactly the same thing that virtual addresses provide. The program reads and writes using virtual addresses. The programmer never knows the actual physical location of that data. So in your head, you should have the following idea. So virtual addresses is nothing but a convenient abstract identifier, the same way as a barcode used in this warehouse. What is the physical address now? Behind the scenes, somehow, the items must sit somewhere. So on a specific aisle, on a rack, on a shelf, inside a specific bin, and these concrete storage spots represent basically the physical memory pages. And virtual addresses, the barcodes, do not reveal where, in which row, in which bank, in which rank in DRAM the data is stored, and you only need that info when you actually access them. When you want to access this item with this label, then you will find out where it sits. There are 4 key issues with indirection and the mapping. The first key issue, what is the mapping granularity? Do we translate at the byte granularity? Do we translate each byte to another byte in the physical address space? Do we use kilobyte large chunks? Do we use multiple granularities? So again, let's take the example of the 2 applications. And we have, again, 2 virtual address spaces and a single monolithic physical address space. Let's take an easy example here. You can think of this physical address space corresponding to the physical memory. In most modern systems, we split both the virtual address space and the physical address space into uniformly sized chunks. So in your systems, for you that you're using Mac OS or Windows, in Mac OS, for example, this chunk is a 16 kilobyte chunk. Mac OS uses 16 kilobyte pages. When you use Windows or Linux, you're using 4 kilobyte pages. So we call them virtual pages, and some people also call them physical frames. I prefer just calling everything pages, basically. I find it a bit more intuitive. So we have the virtual and the physical address space, which is divided into pages. In x86 and x86-64 systems, we're using the standard 4 kilobyte paging, while there's a support for 2 megabyte and 1 gigabyte mappings. And I will explain a bit later how this works. In PowerPC, there are 8 kilobyte, the standard page size, 64 kilobyte, 512 kilobyte, 4 megabyte, 32 megabyte pages. This is from IBM. And in macOS and Apple Silicon, we have 16 kilobyte, which is the standard page size. There are no more information out there about what's the other page size in Apple Silicon. Can you think of any trade-offs between using different sizes? Like, why should I use a 16 kilobyte page size instead of a 4 kilobyte? Why can't I just simply translate every byte in the system into another byte in the physical memory? Does anyone have any idea? Correct. Very good. So this is correct. As I will explain later, we will basically progressively in the lecture, I will show you all these benefits. And this is the key benefit. If I would go for very fine-grained granularity, very fine granularity, like 1 byte, 1 kilobyte, then I need too much storage to translate. So let's take an example of this system. You have a virtual memory size, which is 2 gigabytes, right? So this means 2 to the 31 bytes. And the physical memory size is 2 to the 27 bytes. As you can see, there is a mismatch between the two. The virtual memory size is much larger than the physical memory size. And in this context, the page size is 4 kilobytes. 4 kilobytes is 2 to the power of 12 bytes. So what is the organization? How many bits do I need for the virtual address? I need 31 bits because the size of the for the virtual address space is 2 to 31 bytes. For the physical address, 27 bits. And for the page offset, 12 bits. Why do I need 12 bits for the page offset? Do I need to translate the page offset? No. Inside the chunk, there is no reason why you would translate, right? The internals of the chunk do not need to be translated. So, for example, in this context, you have 2 to the power of 19 virtual pages. How do I find this out? I divide the total bytes of the virtual address space with the size of the page. So I need 19 bits for the virtual page number. And for the physical pages, I have 2 to the power of 15 pages, which means 15 bits for the physical page number. So what then do I need to translate at the end of the day? I need to translate these 19 bits and find their corresponding location in physical memory with 15 bits. So I need to translate these 19 bits to a 15 bits address space. How does this work? For example, I have this specific 32-bit virtual address, and do we need to translate the page offset? No, the page offset is, we can easily find out the location inside the chunk using the last 12 bits. I don't need to translate it. I do not need to translate the last bits in the virtual page size and the virtual page. What I need to translate is the top MSBs to the physical page number. So that's the only thing I need to do. I need to translate these 19 bits to these 15 bits. That's my only job. And we're going to discuss basically how do we do this translation between these 19 bits to these 15 bits. Is it clear why I'm not using the page offset? I do not need to translate the page offset. Okay, cool. So basically, this is the question that your colleague answered before. Where and how can we store the virtual to physical mapping? Do we use the operating system? Do we do it completely in hardware? Do we do it completely in software? And there are many ways to do it. And most modern systems use a page table. A page table, you can think of it as a dictionary. I go to the dictionary, and for a virtual page, I find an entry. And this entry has information about the validity of the page, which means, is the virtual page located in physical memory or not? And second, the physical page number. Oh, I find that my page is valid, the virtual page is valid, which means I can find also what is its physical location inside the main memory. And third, is there any other information I need to know about the virtual page? For example, can I access? Do I have permission to access it? Has it been written by the program? Can I use some reference bits to find out if it has been accessed by the program so that I have a replacement, a very smart replacement policy in the memory? I will explain more later about the page table entry and its structure. You can think of it in this way, the page table. This is the most simple toy version of a page table. It is a contiguous array. It has the validity bits for each page and the physical page number. And the physical page number is basically a pointer. It points to the physical location in the main memory. So for example, the page number 3 is valid, right? The virtual page number 3 is valid. And where is it getting stored in physical memory? In the 0x000. Let's see an actual example of how you would translate. You take this virtual address, right? You have 0x0002. This is your virtual page number. Again, the page offset, we don't need to translate it. So for sure, the physical address at the end will have 47C as the page offset. This we don't need to translate. So we provide the virtual page number as an index to the page table. The way you would basically access an array, right? So you access the second position in not the third position in the page table, and you find, oh, my virtual page is valid, and it is stored in the main memory, in the physical memory. Where is it getting stored? In 0x7FFF. So when I will form right now the physical address, I will concatenate the 0x7FFF with the page offset, which is 47C. So this way I form the physical address, and I'm able to access the physical memory. Is this clear? That's a good approach of doing it. And it's a very, in my opinion, cool ongoing research direction. I will talk about this later. Basically, this is one way of handling things. Instead of using a page table, as you correctly said, you could have a hash function that translates directly your virtual address to the physical address space. This is one way, but it's not the de facto way of doing it, because there are some caveats with it. One, the main caveat of it is sharing pages. If you cannot guarantee that two virtual addresses hash to the same physical location, then you don't have guarantees that you can share pages between two virtual addresses, right? Like with a hash function, you cannot have this guarantee. And another problem is that the moment you remove the fully associative nature, because with a page table, I can basically update the pointer at any point I want, right? If I will move my page somewhere else, I simply update the pointer. But if in the case of using a hash function, I might have collisions in the same physical location, which means that the system becomes a lot more complicated. I will talk about this later, basically. Thanks, though. Nice question. So the question is, where is this page table located and how does the system know it? So the page table is located at the physical memory address specified by the page table base register. So if I know the page table base register, I can figure out quickly what index I need to access based on the virtual page number to be able to fetch it, decode it, find the physical page number, and proceed. So yes, the page table is indexed with a virtual page number, and the page table provides the physical page number. So another example is what is the address of 0xF5F20? The first thing we need to do is find a page table entry that contains the translation for the corresponding VPN by looking up the PTE at this address. So for this virtual address 5F20, the page offset is F20, right? Then I don't need to translate this. Again, the physical page offset is F20. And the virtual page number is 0x0005. So to which index do I need to go to the page table? To the fifth one, 0, 1, 2, 3, 4, 5. And I find out that my physical page is 0x0001, which means that the physical page number is this one. So I concatenate the physical page number with the page offset, and I get the physical address with which I can access the physical memory. Let's see though a more complicated example now. We find out for this address that its virtual page number is 7, right? And we go to the index 7, 0, 1, 2, 3, 4, 5, 6, 7, and we find that the validity bit is 0. So what does the validity bit mean in this case? The mapping is not available. I haven't placed yet this page in the physical memory. I do not know how to translate it and give you a physical address to its location. And I will discuss later how the operating system handles this scenario, where we don't have the mapping to the physical memory. Something about the design of the page table size. So imagine if we had a 64-bit virtual address space and a 40-bit physical address space. So can anyone tell me how big would be the page table in this scenario with a 64-bit virtual address space and a 40-bit physical address space? Like, how big of a page table would I need if I had one single entry for each one of the virtual pages that I have in my virtual address space? Which means that it's, yes, how much? So I have 2 to the power of 52 because I divide by the page size. So 2 to the power of 64 divided by 2 to the power of 12, right? This is the number of pages. And then I will need at least 4 bytes for each one of the pointers. I need 4 bytes for the pointer to the physical address, which means that for each process, I would need around 2 to the power of 54 bytes to allocate the page table. Do you find this reasonable, storing like 2 to the power of 54 bytes for every process? I don't think it's possible. And imagine if the process doesn't use even 0.0001% of this virtual address space, right? So the page table will become very large in this context. And at least part of it, though, needs to be allocated in physical memory. But we will employ a solution to make sure that we don't store the page table parts that we do not need. And this is the multi-level hierarchical page tables. How does a multi-level page table work? So we organize the page table in a hierarchical manner, such as only some parts of the page table have to be allocated in physical memory. Only the parts that correspond to virtual memory locations that are being used by the program. If a virtual memory location is not used by the program, then I do not need basically its entry in the physical in the page table. How does this work? So you remember the virtual address from before, right? Okay, the page offset remains the same. So we're using a two-level translation process in this scenario. We take the page table offset from the virtual address and the page table number. So the page table number, you can think of it as a first order page table that tells us, this part of the page table is valid or invalid. And based on the validity and the validity of this part of the page table, these second level page tables will be allocated or not. So there is a scenario here where only one of these first level page table entries will be valid, which means that only one of these second level page tables will be allocated. Why is this the case? Because my virtual memory, the virtual memory that my program is using only corresponds to this first entry. It doesn't touch any other entry from these 9 bits. And if this is the case, I would not need to store many of the second level page tables. Any questions with respect to that? It's a more complicated concept. I will explain an example so that we are more on the same page. So how does this work? We have the page table number. The page table number tells us, oh, you're going to go to this region of the page table. So imagine this small table as covering a big portion of the page table and telling us, oh, this portion of the page table is invalid. You don't need to allocate it. The other portion of the page table is valid. You need to allocate it. For example, this scenario, we only have two portions of the second level page table being valid, the ones with a validity of 1 here. So we first select the portion that corresponds to our virtual address. For example, here we have the page table number being 0x0. So we go to the first entry, right? And we're saying, oh, this is a valid page table region, which means that you need to allocate the second level of the page table. So we get the pointer to the second level of the page table, and we find out the final pointer to our physical address. So to give you an understanding, if your program is mostly using the least significant bits, right, then the page table number will be usually 0x0, which means that you would need only one portion of your second level page table to be allocated all the time. Is that clear? So you can think of it as basically you can map it very easily to a dynamic tree data structure which corresponds to trees or binary heaps or something similar, right? Where you do not need to store every pointer if there is no connection to the bottom layer, right? And if we had n different levels in the page table, how many page table accesses would we need? N. Because I could also apply recursively the same technique for this page table, right? If this page table would end up being very large, this part of the page table, then I would do this recursively and add another level of indirection here, so that I basically do not need to allocate parts of this page table as well. And that's what most modern systems do. In most modern systems, you break the virtual address into 4 parts, 4 9-bit parts, and using the page table base register, you're accessing directly the first level, which is always allocated in memory. But you're accessing 4 levels until you find the final physical address. So you're basically performing 4 memory accesses in most modern x86-64 systems to retrieve the physical page number. So can you think again of this concept of page size and see how it would affect the page table and how the process of looking up the page table would change if I use different page sizes? Does anyone have any idea? For example, the second level of the page table in x86-64, each entry of the second level covers 1 GB of memory. If I'm using a 1 GB page size, how many hops do I need in the page table to retrieve my data? If the second level covers 1 GB and I'm using 1 GB large pages, then I need only 2 hops. I need to access the first level and then the second level. And then I stop because I'm not using 4 kilobyte pages. I'm using 1 GB pages. If I'm using a 2 MB page size, then how many hops do I need to retrieve the physical translation? I need 3 hops. I will stop at the third level because, again, my system is using 2 MB pages, right? In most modern systems, I need 4 hops because the standard is I'm using 4 kilobyte pages. So to think of it in a better way, these 2 MB here, there are entries that correspond, each entry covers a 2 MB region, right? So one entry basically corresponds to a 512 multiplied by 4 kilobyte, which is 2 MB region. So the last level gives us the granularity. It goes into a deeper and deeper and deeper and recursively exponential granularity, basically. This is how it looks in x86 64. The second level maps 1 GB physical frames, the third 2 MB frames, and the last one 4 KB frames. And yes, when we're accessing, when we're using 2 MB pages, we only need to perform 3 memory accesses, right? Which makes the process of finding the translation a bit cheaper, right? Because I do not need to go to the 4th level. If I'm using 1 GB pages, then the process becomes even cheaper because I need to perform only 2 accesses. I need to access only the 1st level and the 2nd level. The 2nd level, each entry in the 2nd level covers a 1 GB region. So I could translate directly using the entry at the 2nd level. Is that clear to everybody? Cool. So using a larger page size requires fewer PTEs, fewer page table entries, it saves memory space, and leads to faster page table walk. On the other hand, we need much larger transfers to and from the disk. If we decide that we're going to move a very large page to the disk, then the time it takes to move this page becomes larger. If I want to move simply a 4 KB page to the disk, it's much cheaper than moving a 1 GB page to the disk. This way, we would waste bandwidth and energy. And this way, we would reduce performance if we need to move such large page sizes. Another disadvantage is the internal fragmentation. So can someone tell me what would happen if the system always allocates 1 GB data for me, even though I use only 1% of it? Like, what would happen in your laptop right now if this would happen? It would crash, right? Because if the system, if I need 1 kilobyte of data and the system gives me always 1 GB, then it would basically very easily waste space and not have memory, not utilize memory properly. And at the end of the day, it's going to say, okay, memory is full, without the memory being full, actually, because from this 1 GB that you're allocating, the application is using only 1 kilobyte. So you made the translation potentially much faster, but you're underutilizing memory, which is basically wasting memory capacity. So this was the first challenge with the page tables, right? They become very large. And we discussed how we can solve it with the multi-level page tables. So the second challenge is the following. For each data access we're doing, for each virtual address that our program needs to access, then we need at least 2 memory accesses in this system, right? The first is to perform the address translation, to perform the read to the page table. We need to go to the page table and read it to find out the physical address. So the second access we're doing is the physical address access. So we would need 2 memory accesses to service an instruction fetch or a load store, with a data load store, which greatly degrades execution time. So the number of memory accesses, again, do they depend on the structure of the page table? Yes. If I'm using a 1 GB page, then I would need 2 accesses. If I would use a 2 MB page, I would need 3 accesses in this 4-level page table. If I'm using 4 KB pages, though, which is the worst scenario in terms of address translation latency, I need to perform 4 accesses in the beginning. I translate, I get the physical address, and then I am accessing the physical memory. So you would need in total 5 memory accesses to perform my data fetch. But modern systems use ways to speed up the translation process. Another real-life example of what is the page table, basically. So the warehouse management system stores mappings like, oh, this barcode is in AL4, in rack C, in shelf 2, in bin 6. This other barcode is stored somewhere else. So this is the role, basically, of the page table. It maps the virtual page numbers to the physical page numbers and defines where every piece of data actually lives. And it also provides isolation. So 2 barcodes can't accidentally point to the same item unless they're explicitly shared. The page table makes sure that we don't access another application's physical memory, right? And the programs are not exposed at all to the page table. The programs use barcodes. Only the page table knows the real locations. Let's see right now how we perform the address translation. To support virtual memory, we need basically both hardware and architectural hardware and software support. So the page table resides in the memory, and it is the job of the software of the operating system to populate the page tables, to decide what to replace in memory, to change the page table registers on context switch. Why do I need to change the page table register? Because I need to load up another application in the system, which requires another page table. It also needs to ensure correct mappings. And one of the biggest questions is, how does the CPU on the fly discover the virtual to physical mapping? So the CPU simply receives a virtual address, right? Then it needs a way that it discovers the virtual to physical mapping for this specific address with the process of address translation. How does this happen? The core, your core here, that's in the system, on the CPU, it ships the virtual address to the memory hierarchy. And the memory hierarchy right now stores the page table. The page table is stored in your main memory, right? And the page table responds, okay, this is the page table entry for this specific virtual address. You can now access the physical memory. So the page table contains an entry for each one of the virtual pages. The OS needs to guarantee this, that for every available data, it needs to contain its physical memory location, right? And what you retrieve back at the core level is the page table entry. And the question is, what is the page table entry? This is part of the instruction set architecture, basically, in most modern systems. You can think of it as a packet with headers. It's an 8-byte packet with headers. So first, it contains the physical page number. So we have the physical page number, which means where is data stored in, if data is valid. We also have protection bits. I will talk later about how virtual memory offers the concept of memory protection as well. We also have reference bits. Reference bits help us to figure out if this piece of data, this page, for example, has very high access frequency. Do we access this page very frequently or not? We also have a dirty bit that says, do we need to write the page to the disk if it's evicted from memory? Did anyone write to this page so that I need to write back to the disk if needed, if I evicted from the physical memory? It also has the validity bit. Is the page actually stored in the main memory? The validity bit tells us, oh, this is not stored in the main memory. That there's no way you can access it, right? And this is what I'm going to discuss first. The scenario where the validity bit is 0. Validity bit 0 means that the virtual to physical mapping is not available yet. We have the application and the virtual address space. And the application wants to access data in this specific page, right? And somehow, when the core tries to access it, it finds out that there is no physical location in memory where my data is mapped to. So somebody needs to map it. And the core immediately raises a fault, which is an exception. And it says, oh, the virtual address is not mapped to the physical memory. So somebody needs to take over and make sure data is mapped there. Who takes over? The operating system. So the operating system takes over and handles the memory allocation. It needs to place my data somehow in the physical memory. I'm going to discuss how it does that. First, we stall the application. The application is stalled. It cannot run any other instructions because it needs to service this type of fault exception. And the operating system, in the case of a minor fault, which I will dive deeper, simply tries to find free space in the physical memory. And one minor fault is the simplest type of fault, and you can service it in the order of microseconds. So if the data has not been assigned a location in physical memory, but also it's not in the disk, then the page table entry indicates that the virtual page is not valid, and the access to such a page triggers the page fault exception. So the OS is invoked to handle the data mapping. Other processes can execute, right? My process is stalled. And the OS has the full control over the page placement. It can place the page wherever it wants. So my question for you is, if the data does not need to be fetched from the disk, why do we have minor faults? Like, can anyone think of a scenario where a minor fault happens? Like, data does not need to be fetched from the disk, and the mapping is not ready yet. Can anyone think of when this happens? The first type of minor fault is the anonymous pages. For example, when you write your C programs, your Python programs, right? There are pages which are simply allocated by you, virtual pages allocated by your program, but they're not initialized yet. And they're also not backed by a file. So in this scenario, it's some sort of ephemeral data, for example, your application is using, and you can see an example here, right? So I am doing a malloc in C, right? This is an anonymous page. Why is it anonymous? Because it's not backed by a file. And I'm doing a write. I want to initialize my data. I'm doing data of 0 equals 0. This means I'm going to the first page of data, and I'm saying write 0 there. But what happens here? There's no mapping established yet. And with no mapping established yet, the operating system says, okay, I do not have a location yet. I need to allocate data for this piece of array. Another type of minor page fault, which you may have seen in your operating system courses, it's a copy on writes. We may have, do you know, how many of you do know what is a clone or a fork in operating systems? Yes, okay. So when you do a fork, and you have a parent process and multiple children processes, right? So they initially share the memory pages, especially if you do a vfork, for example. But when a process attempts to modify a shared page, so they all pointed to the same physical location, right? But when someone needs to modify a shared page, then we have a page fault. Why? Because nobody has write access to this page. So we need to basically take this page and copy it somewhere else, and give full access to the child that wants to write to this page. So this basically triggers the creation of a separate copy of the page for the modifying process, only for the modifying process. This is a very simple example that I crafted yesterday. So let's say that the parent process is doing x equals 10. X corresponds to a page, right? It's a virtual page. X resides inside the virtual page. The process forks, the parent process forks, and then if you're the child, go and write 20 to X. This is basically a write on top of a shared page. And this would trigger basically the copy on write, which would trigger a page fault. Is it clear to everybody? Cool. This is a simple case, the minor page faults. So there are also major page faults. In the major page faults, we need to fetch data from the disk, which takes order of milliseconds, and then find free space in the physical memory. This is a sort of an expensive fault. You can think of it as a miss in the physical memory. Data is not anonymous, it's not a copy on write, data is probably backed up by a file, or it's in the swap space, and there is a miss in the physical memory. So if the page is not in the physical memory, but in the disk, then the page table entry indicates that the virtual page is not in memory. Access to such a page triggers the page fault exception, and the OS is invoked to move the data from the disk to the memory. So other processes can this way continue executing. OS has full control again over the placement, and the way this happens is the following. Let's say that before the fault, the CPU which is trying to access this black location, right? And while translating, it finds out in the page, using the page table, that this piece of data, this page, is stored in the hard disk. And I cannot access the hard disk directly. There's no way that this can happen in the system, right? So what do I need to do? The operating system gets invoked, it handles the fault, and it moves the page. Instead of a black page right now, I have a blue page, because the data has been moved from the disk inside the main memory, and the page table points to the location in the physical memory. Now, the operating system gives control back to the application, and it says, okay, I moved your data in the memory, and you can now access it. This is a more detailed example of how we service this major page fault. So the processor basically signals the I/O controller. The I/O controller says, okay, I will read block of length P, starting at disk address X and starting at memory address Y. This is done off the critical path. Basically, the I/O controller says, okay, move this page inside the memory transparently from the CPU. The CPU doesn't need to participate in this transaction. Can someone tell me why I don't want the CPU to participate in this transaction? Like, why would I not make the processor participate in this transaction? Is there a reason? The basic reason is that if the processor participates in the transaction, then I will start polluting the caches of the processor of the core with data which participate in the migration process. And I don't want that. I want the processor to be able to keep its caching resources for what it's running at the moment. I don't want it to participate in this process. I want the processor to simply, the OS to simply invoke the transaction from the disk to the memory, and then at some point get done with it and signal to the processor, oh, it's ready right now. So when this disk to memory read occurs, we have direct memory access, and the controller at some point signals completion. And when it signals completion, the processor gets a signal and says, okay, I can basically continue running this process because the disk to memory IO has completed. So data is memory. I can access it right now. The program can continue running. An example again in the warehouse. So the page table, the page fault means that the item is not currently in the warehouse. And so sometimes the barcode is valid. Our program has virtual addresses, but the item isn't in the main warehouse. It might be in some sort of very deep storage, right? So we want the warehouse robot to fetch or make space in order to basically create space for us and bring our item there. And the workers who want this item, who need this item, they need to wait before they access it. And this is basically a page fault. The virtual address is valid, but it's not currently mapped to the main memory. In some cases, you may need to fetch it from the disk. In other cases, you may not need to fetch it from the disk. But the operating system needs to handle the creation of the virtual to physical mapping. The page table then is updated and the work continues. And if we want to access pages which are in the disk, which are swapped out of the memory, that's a very painful process, equally to the waiting for the robot to fetch the item from the deep storage. So when the operating system handles the page fault, what does it need to do? It needs to store and update the virtual to physical address mapping. How? By updating the page table which resides in the physical memory. What happens right now in a scenario where I would need, for example, to bring my data from the disk, but the memory is full? What happens in a case that caches are full in the system? It's the same analogy, right? When your cache is full and all the tags of all the ways of a set are full, then you need to replace something. So the operating system takes over again and says, oh, I need to replace a physical page from main memory to make space for what the application needs, for what I need to bring from the disk. And my question to you is, can we do true LRU in memory? Like, can we have basically an order of the true least recently used order in memory? No, it's very, very expensive. Having a true LRU for memory. It's even very expensive for the caches, right? It's also very, very expensive for the memory because there are many, many possibilities of ordering. So we cannot do that. We will try to approximate LRU basically. And one way to approximate LRU, one of the oldest algorithms, is called clock. There are a lot more sophisticated algorithms. There's clock plus plus, I think. Harsh, how do we call this? Clock plus plus. Clock plus plus, yes, which also uses the access frequency as a feature to make a decision about which page is going to be replaced. This is called the ARG algorithm as well. It's published in FAST 2003. And I'm going to explain clock very quickly. So as you can see, literally a clock, basically. And the first thing the operating system does is it keeps a circular list of physical frames in memory, which means that for every physical frame, it stores a bit. It's a bitmap. And there is a pointer that points to some location in this bitmap. The pointer is always to the last examined frame in the list. For example, if I accessed for the last time this specific page, then I will keep the pointer here. When a page is accessed, set the R bit in the PTE. What is the R bit in the PTE? It's the reference bit, which means the bit that tells me this page has been accessed by the program. So the operating system should know this, so that this page is hot. It's recently accessed by the program. So don't evict it, basically. And once the R bit is set in the PTE, when a frame needs to be replaced, let's say that all these bits are 1, right? Or let's let's say forget about that. So let's say that the memory is full, right? And let's say that I need to find out right now using the clock which page to replace. So the clock starts ticking right-wise. And I'm saying, okay, has this page been referenced in the past recently? No. Then I will replace this page. If a page has been referenced in the past, like 1, I will make the bit 0, which means I reset it. So basically, in a nutshell, what am I doing? I'm giving an opportunity to stay more in memory for the pages that have been recently accessed, and I'm not giving any opportunity to the pages that have not been recently accessed. That's what clock does. It's basically a binary decision based on the recency, based on how recently this page has been accessed. Is this the best we can do? I don't think so. So there are many more factors which you need to take into account to make such decisions about what to replace and what not. The access frequency. The state doesn't take into account the access frequency, right? How frequently do I access? Like how recently I access this page doesn't necessarily correspond to how frequently I access a page. So you can think of the cache versus page replacement as an analogous to the physical memory being a cache for the disk. And you have seen a lot of these in the cache replacement course, the cache course, cache subsystem course, part of the lecture. What is the difference? The difference is the speed of access, right? Accessing the cache is much faster than accessing the main memory. Second, the number of blocks in a cache versus physical memory. Physical memory is a lot bigger, it has many more blocks, even though the granularity of access is at the 4 kilobyte. Another thing, the memory has a tolerable amount of time to find the replacement candidate. Imagine if for every cache replacement, I would spend 1 millisecond to find its replacement candidate, and then the program would run forever, right? However, in the case of replacing a memory, I have a much higher tolerance when it comes to waiting for the replacement. Also, the role of the hardware versus software. In the one scenario, the replacement policy in the caches, it's happening at the hardware level. We have a hardware circuit that does the cache replacement. In the other scenario, we have software which is responsible for taking over and handling this replacement. You can think of the analogy this way. We have blocks in caches, pages in memory. Block size in caches, page size in memory. Block offset in caches, page offset in memory. Misses in the caches, major page faults or minor page faults in memory. Indexes in the caches, virtual page numbers in memory. Metadata and tag storage in caches, page table in virtual memory. We have data stored in the caches, we have physical memory and the physical devices in the memory. Let's have a 5-minute break and then we can continue. And then I'm gonna dive deeper into the memory protection aspect of virtual memory. It says, sorry? No, it's DRAM, right? It's not. So external disk doesn't mean I put a USB in my laptop and that's the external disk. So I use the disk of the system as the swap, basically, where I can remove pages. I can remove pages basically from my memory, from my DRAM, and place them in the hard disk of my system that the system is using. So your files exist basically in the. Okay, the kids are back. Yeah, sure. Hmm. Okay, sure. So each process has its own register. So each process has one register that points to exactly what you said, which is the base table. Yes, it has the first address to the first level of the page table. So when you context switch, when you want to switch the process that you run on the CPU, you need to basically change this register. There's also a hardware register that gets updated using the page table register, which lives in software, right? Cool. So the second part is about memory protection. So when do we need memory protection? We need memory protection when multiple programs or processes or threads or entities basically execute programs concurrently. Each process has its own page table, and each process can use its entire virtual address space without worrying about where other programs are. So when you write your program in your laptop, you don't care about what Google Chrome is doing while you're running your program. So a program can only access physical pages mapped to its page table. It's basically cannot overwrite the memory of another process. This provides protection and isolation between processes, and this enables access control mechanisms per page. So let's see these examples. We have each process with its own virtual address space. And this simplifies a lot the memory allocation, sharing, linking, and loading. Why? Because each process has its own virtual address space. And when I translate, I find out that my virtual page 2 points to physical page 7, while virtual page 1 from application 2 is pointing to the same location. What does this mean? If they're pointing to the same location, data is shared. We're using a common library. In this case, it's read-only. No one of these two virtual pages can overwrite the page 7. Why? Because it's read-only. If I want to overwrite it, we will handle it the way we discussed before with the copy on writes. I would create another copy, and I would make VP2 point to another location. I cannot overwrite this page. It's read-only. So virtual memory serves a second purpose in modern systems, which is the access protection and the control. Real-life example, warehouse. Memory isolation means workers can't access the wrong items. So workers, basically, we issue permissions to them. And we're saying some can only pick from section A. Some can't open locked bins. Some can access restricted aisles. And basically, this is memory protection. Processes cannot access memory they do not own. And even if two programs use the same virtual address, they map to different physical pages unless they share data. So the page level access control, how does this work? Not every process is allowed to access every page. It needs supervisor level privileges to access system pages, for example. Like your programs, when you run a program in your laptop, you're not allowed to read or write or execute in pages that belong to the operating system. That's impossible. You may also not be able to execute instructions in some pages. So some pages contains programs, right? But not everyone should be able to run a program. So the idea here is that we will store access control information on a per page basis in the processes page table. And this way, when we do the translation, directly after that, we can also do the access control. So this way, virtual memory serves two functions today. Address translation for the illusion of a very large physical memory space with programmer transparent memory management, as well as access control, which offers memory isolation and protection. So what we discussed before, we have the virtual page number, we translate, we take back the physical page number. I will enhance it right now with memory protection. How? We take the virtual page number, first we translate, then we perform the access control, and then we retrieve and we're able to access physical memory with the physical page number. Again, in the same example, we have two processes and we extended the page table entries with permission bits. Right now, these two page tables, you can see two different page tables here, have different processes for each page. And we want to check the bits on each access during a page fault or during an access, right? When we translate. So if we violate any of these access bits, then we generate an exception. That's how a segmentation fault happens in your system, right? When you're trying to access a virtual page that you may have not allocated yet, and it's not your own, and you bypass the bounds of your array, that's where a segmentation fault rises and says, you don't have access to this page. What are you doing, right? So in this context, process I, for example, is using two virtual pages, virtual page 0 and virtual page 1. So virtual page 0 corresponds to physical page 6, right? And as you can see, physical page 6 is shared with VP0, virtual page 0 of process J. Do both processes have the same permissions to this page 6? No. The first process, process I, can read from the page, but not write to the page. While the second process, process J, can read to the page and write to the page, which means it's the owner, basically, of the page. I'm the owner of the page, and I let you simply read from it. That's not true, for example, for page 1 of process I. Page 1 corresponds to physical page 4, and page 1 has both read and write. The process I in page 1 has both read and write permissions. That's how the privilege levels looks in x86. We have applications running in the protection link 3, some operating system daemons and services running in level 2 and 1, and the operating system kernel running at level 0. This sort of abstraction differs a lot from operating system and across architectures and operating systems. And for example, in x86, we have these 4 privilege levels. In ring 0, we have the highest privilege. The operating system is running. In ring 3, we have the lowest privilege where user applications are running. And supervisor, kernel, you can call this in modern terminology, is basically in ring 0, where the user is in ring 3. Let's take a closer look at the PDE and the PTE. What is PDE? It's the level before PTE. So it's the last from the end level of the page table. So it's the one that contains 2 megabyte translations, right? In the x86 system, which means 32-bit systems, we had only 2 levels in the page table. So the first level corresponds to 2 megabyte pages. And what does it store? A pointer to the next level, right? And some flags. The flags are these protection and access control bits. And after I resolve and I find out where I point to the last level, I get the PPN, which is the final address, the 4 kilobyte address, as well as the flags, which correspond to access control bits at the 4 kilobyte granularity right now. This is an example. For example, we might store if the data is present, if this is user or supervisor. For a page, I might store information. Is this page belong to the supervisor or does it belong to the user? Can I read to it with the first bit or write to it? Is the page present or not? Should I write through or not? And many more of these. For example, the last level page table entry corresponds to only one page, like the access control bits of the last level page table entry corresponds to only one page worth of access control bits. You cannot go beyond express access control beyond the 4 kilobyte granularity using the last level page table. However, we could do the following trick, right? We could use the first level, which expresses access control bits at the 2 megabyte granularity, We would express also control bits at the 4 kilobyte granularity and basically perform an AND operation between these two bits, between all the access control bits, to find out the final granularity of access control. I'll give you an example. Let's say that for this specific page, right, the user says that it's read-only. It's accessed by a user and it's read-only. And the 4 kilobyte entry says it's user and read-only. So of course, it's very clear, right? It's a user read-only page. Let's go to the third one, to the one from the end, last one from the end. So it's a user page with read-write permissions. So the whole 2 megabyte page is read-write, the permissions of the whole 2 megabyte page. But the corresponding 4 kilobyte page for this data is a user space and read-only. So at the end of the day, we will have a user space page with read-only protection. Why? Because the 4 kilobyte dictated that it's a read-only page. Even though the 2 megabyte region is generally read-write, this specific page is a read-only page. And this is what basically dominates in the final control access. This is not very important because it changes a lot across architectures, operating systems, and page table designs. That's why I don't want to spend a lot of more time on this. But I'm going to go to an interesting observation. So let's say that somehow, somebody may have talked about it, that your hardware is unreliable and someone can flip the access protection bits. So why do we want to do that? Because the user level program can gain supervisor level access. Let's say access to all the data in the system. Because if one of these bits was 1, I can flip one bit, right? I make one of the pages a supervisor page. Then I can flip the access control bit from the user to supervisor. And then the question is, can this happen? Does anyone know how this can happen? Okay, you know, I know you know. So if you remember RowHammer, that predictably induces errors in most DRAM memory chips, that's a very cool way that this can happen. How? One can predictably basically induce bit flips in most commodity DRAM chips, right? And the authors have tested more than 80% of the tested DRAM chips, and they have shown it's very vulnerable. And this was one of the first examples of how a simple hardware failure mechanism can create a widespread system security vulnerability. And this has been shown here in the news, basically, in the Wired. How does RowHammer work? I'll give you a recap. We have rows in our bank, have a word line. We open up a row to the high voltage. Then we close the row. We open the row. We close the row. We hammer this row. And what do we cause to the neighboring rows? We cause bit flips. The neighboring rows, we call them victim rows. And by repeatedly reading this row, this hammered row, enough times, we can cause disturbance errors in adjacent rows in most real DRAM chips that you can buy today. And there is much research coming from the group in this direction. How would this look like in a program? I would move X into a register, move Y into another register, flush them from the caches, and then do the same again. What does this cause? I avoid cache hits. Why? Because I flushed X from the cache. I avoid row hits to X. Why? Because I read Y in another row. So how does this look like? Y, X all the time. I do this all the time. And I cause bit flips in the intermediate and the upper and bottom rows. Basically, by accessing X and Y all the time, by hammering both of them, I am able to cause bit flips in the neighboring rows of X and Y. Yeah, the paper was also published in ISCA 2014. At the same time, there was the Project Zero team at Google who tried to also show this security, like I think they wanted to approach it from a security vulnerability point of view. So I'm going to show you right now how the original RowHammer attack from Google was performed. This was from Mark Seaborn and Thomas Julien's Black Hat 2015 talk. So the kernel exploit here is the following. We have x86 page table entries, which are trusted. So they control access to the physical memory. A bit flip in PT's physical page number can give a process access to a different physical page. And the aim of the exploit is to get access to a page table and give access to all of physical memory. This basically maximizes the chances that the bit flip is useful. This way we can spray physical memory with page table. How do I achieve this? By spraying physical memory with page table. I will show you how. And check for useful and repeatable bit flip firsts. How do the authors did that? In the virtual address space, they allocate a page and then they map it in the physical memory, right? So the question is, what happens when we map a file with read-write permissions? The page table gets created, right? The page table, and the virtual address corresponds to this page table entry, which points to the physical location, right? That's what we discussed before. So the question is, what happens if I start creating virtual regions that all map to the same physical page, to the same page backed by a file? I will create many of these page tables that simply point to the same physical location, right? What happens if I can fill all memory with page table entries? Basically, what's the problem here? The problem is that, okay, I filled up the whole memory right now with page table entries, and each of them points to page in the same physical mapping, right? All of them point to the same physical page. So if I had a bit which in the right place flips in the PTE, then the corresponding virtual address, I would make it point to a wrong physical page with read-write access, because I have read-write access to this page, right? If I would flip the bit of the physical frame number, then I could make it point anywhere I want, right? So the chances are that this wrong page contains a page table itself. So if I flip the bit inside the page table and make it point somewhere else, if I have filled up the whole memory with a page table, where would it point? It would point to another page table. So this way, I would give the attacker the possibility to read and write page tables. How would this happen? Basically, the attacker would read and write to whichever page table it wants, and this way they could map any memory to their read and write location. Does anyone have any question on this? It's a very interesting type of attack. Can discuss more also if you want. So the security implications of RowHammer, it's basically as if we want to break into an apartment by repeatedly smashing a neighbor's door until the vibrations open the door you were after. So basically, you smash the neighbor's door, you open the next door because of the vibrations. And researchers have shown how you can also perform remote software-induced fault attacks in JavaScript with RowHammer. And as a takeaway, if your hardware is unreliable and you have higher level security and protection mechanisms that might be compromised, right? So in the root of security and trust is at the very low levels. In the hardware itself, like for example, RowHammer, Spectre, Meltdown, and very recent key examples of this. And the question is, what should we assume that the hardware provides? How do we keep the hardware reliable? How do we design secure hardware? How do we design secured hardware while maintaining high performance, high energy efficient, low cost, and convenient programming? There is plenty of exciting and highly relevant research questions here, and I will discuss later about research opportunities in the lab to work with us on such topics. Some other issues in virtual memory right now. So we discussed the first one, right? How large is the page table and how do we store this? We discussed that using multi-level page tables is one way to deal with that. The second, and to me, in my opinion, one of the most important problems of virtual memory is when I want to access the page table and I want to perform translation, how do I speed this up? How do I speed up the process of translating and performing the access control check? So how fast is the address translation? How can we make it fast? So the idea is that we're going to use a hardware structure that caches page tables, the data of the page table, to reduce the number of memory accesses to look it up. And how does this work? The core sends the virtual address to a unit, which we call the memory management unit. It's the hardware unit responsible for address translation. And the memory management unit has one job: communicate with the memory hierarchy, load the page table, and perform address translation whenever it's needed. How does the memory management unit look like? There is one memory management unit per core. One of your cores right now in your systems, phones, laptops, desktops, they have one memory management unit, each one of them. And it has 3 key components. This is not true in all systems. So we have a translation lookaside buffers that cache recently used virtual to physical translations directly. I give the virtual page number, the virtual address, I get back the physical address immediately. I do not need to access any page table. Page table walk caches. When we have a multi-level page table, as we discussed before, we need to go pointer by pointer by pointer. This page walk caches gives us fast access to these intermediate pointers so that we do not need to fetch them from the main memory. And then there is a hardware page table walker. If the TLBs and the page table walk caches do not work, right? I do not find any information about the page table in the MMU, then I have the hardware page table walker that says, okay, I am the hardware circuitry that is basically gonna look up the page table for you and retrieve it from the main memory. That's how an MMU looks like in an Intel Skylake processor. You have 2 L1 TLBs, first level TLBs, one that caches translations for instructions and one that caches translations for data. If we miss in both of them, then we access the L2 unified TLB. What's the second level unified TLB? It caches translations for both data and instructions. If we miss in this L2 unified TLB, we trigger the page table walker, which starts generating the lookup process for the page table, for the multi-level page table. If any intermediate step, any intermediate pointer is found in the page walk caches, then we retrieve it from there. Otherwise, we access through the memory. Let's go to the components one by one. So the idea with the TLBs is that you want to cache the page table entries in the hardware structure in the processor to speed up the address translation. So it's a small cache of most recently accessed, most recently used page table entries, and it reduces the number of memory accesses required for most instruction fetches and load stores to only one TLB access. The warehouse example. So the TLB, you can think of it as the worker's pocket notepad. So the workers cannot check the database for every single barcode because it would be too slow, right? They would need to go to the inventory, check the database, find out where the item is, and then do this for every item. Instead, they keep a tiny notebook of the most recently used barcodes. This way, they know the barcode to location mappings very quickly because they're written in the tiny notebook. And this note, you can think of it as a translation lookaside buffer. It's a small, fast cache of translations. And if a translation is found in the TLB, we have an extremely fast access. If not, it must check the slower warehouse database, the page table, to find out the virtual to physical translation. The TLB has a very similar structure to what you have seen in the caches. So we basically form an index, a tag, the data, which is the page table entry in this scenario, to be able to access it. We take the virtual address, we access specific set using the index, we perform tag matching, and then at the end, after we retrieve the data, we form the physical address. So there are many translation requests, though, which are going to miss in the TLBs. We might not find all our translation requests hitting in the TLB. And in this scenario, we need to access the memory to find the corresponding page table entry. This is the process we call walking the page table at the hardware level. And this has, as I will show you later, a very large performance penalty. And if we do the better job in TLB management and prefetching, TLB prefetching, we could reduce the TLB misses. And one of the big questions is, who would handle the TLB misses? Hardware or software? So the first approach is we will handle the TLB misses at the hardware level. Can anyone tell me an advantage of doing this compared to handling the TLB misses at the software level? At the software level, we would need to trap, stop the process, the OS handles that miss, it adds the corresponding entry in the TLB and then continues. What would be an advantage of doing it directly at the hardware level? That's one, yeah, that's true, because you would not pollute the cache with the operating system running, right? But that's a secondary benefit. The first benefit is that you basically can do it very fast, right? You do not need to invoke the operating system. You have a hardware unit, walks the page table, it fetches the page table entries, inserts them in the TLB, and yes, if the TLB is full, it simply has a hardware circuit to replace the entry with another one, right? And it's done transparently. You don't need to change the system software, right? You have a hardware circuitry responsible for this. Also, you can employ specialized structures and caches, page table walkers and page walk caches. In the software managed scenario, how do you do this? You raise an exception, the operating system does the page table walk, the operating system fetches the page table entry, and inserts and evicts the entries in the TLB. So in the hardware managed TLB, no exception on TLB miss. The instruction simply stalls, waiting for the translation. We have independent instructions, which also may experience TLB misses, which can still run because I didn't trap to the operating system. I'm still running user space code. And there are no extra instructions brought into the caches, basically what you said. I do not pollute the caches, basically. What's the problem, though? The page table is fixed. If I created a hardware circuitry to walk this type of page table, then I need to stick to this type of page table. The operating system cannot reorganize the page table in any way it wants, right? Because I have a fixed hardware circuitry that is part of the ISA and says, okay, I need the operating system to have a contract with the hardware that this is the page table design. The second is the software managed TLB. What is good with that? The OS can define the page table organization. Hardware doesn't need to know anything about how the page table works. You can also potentially have a more sophisticated TLB replacement policy. Why? Because you can run software. You can replace entries in software. You don't need to specialize a specific circuitry in hardware to perform the replacement. But as you correctly said, you need to generate an exception, which means that we have performance overheads from pipeline flashes, handle executions, and extra instructions and data brought into the caches to execute this handling of the page table walk. So let's see how the L1 data TLB looks like in a Skylake processor. The data TLB has support for 4 kilobyte, 2 megabyte, and 1 gigabyte pages. For example, it has 64 entries for 4 kilobyte level translations, 2 megabyte level translations, and 1 gigabyte level translations. And the virtual to physical mappings are inserted into the corresponding TLB after a TLB miss. And what does corresponding mean here? I will explain. So during a translation request, all 3 L1 TLBs are looked up in parallel. Why? Because we do not know the page size a priori. We do not know what is the page size before we access the TLBs. We simply need to make assumptions about the page size. So a second benefit of using larger page sizes here is that we will potentially have fewer TLB misses. Why? Because we can pack into a single entry of the TLB a much larger area being covered. So we have 3 TLBs here, one for the 1 gigabyte pages, one for the 2 megabyte pages, and one for the 4 kilobyte pages. So why do I need to form 3 different indices? Can someone tell me? I cannot access all these TLBs with the same index. Why? Because the page size is different. And if the page size I assume to access each TLB is different, I need to change the offset as well. In the one case scenario, the offset is 12 bits. In the other case is 21 bits. In the 1 gigabyte scenario, it's 30 bits. If the offset changes, what also changes in the way I access a cache or a TLB? The index. So I basically access these TLBs in parallel with different indices being formed by different page sizes. And I find out, oh, is maybe my translation a 1 gigabyte translation? Is maybe my translation a 2 megabyte one or a 4 kilobyte one? Is that clear to everybody? That's the reason why I need to change the index, because the page offset changes. In the one scenario, the page offset is this, and the index is these 2 bits. Why these 2? Because there are 4 sets in the L1 TLB for 4 kilobyte. Then I proceed and I use more bits for the page offset. I use 20 bits here, 21. And I use only 1 bit for the index for this TLB. Why 1 bit for the index? I only have 2 sets. For the third index, how many do I use? It's 1 gigabyte to the power of 30 bits. I use only 1 bit for the index. Why? Because again, this L1 TLB that supports 1 GB translations has 2 sets only. So I need 1 bit for these. Let's say that I missed in all this. I didn't find anything in my L1 TLBs, right? So I need to access the L2 unified TLB. And we have 2 separate L2 TLB structures, one that stores both translations for both 4 kilobyte and 2 megabyte data, and one that is separate and stores translations for 1 GB pages. As you can see, the L2 TLB is much, much larger compared to the L1 TLB. It's almost 10 times larger. Oh, not 10, 20 times larger. And the question is, how can the L2 TLB support both 4 kilobyte and 2 megabyte pages using a single structure? Does anyone have any idea? What is one way of accessing the TLB assuming a page size, basically? There's not enough public information to give you the exact algorithm that this happens, but they have some guesses. And the guess is that we will probe the L2 TLB in 2 steps. We will first assume that the page size is 4 kilobytes. After we assume the page size is 4 kilobytes, we form the offset and the index. The index in this scenario is formed and we access the L2 TLB, the corresponding set. If we have a tag match, this means that the page is a 4 kilobyte page and it's a hit. But if we do not match, we go to step 2. And in step 2, we change the assumption about the page size. We assume right now that the page size is 2 megabytes, which means that I will recalculate the index, recalculate the offset, and access again the L2 TLB. And if the tag matches, it is a hit. If the tag does not match, it's an L2 TLB miss. And the general algorithm, as you can think of it, is that like if I have n page sizes, then I would do this for n different page sizes and access the TLB sequentially for each one of them, right? So this is something similar to the concept of associativity in time, which is also called pseudo-associativity. This exact concept can be used with the caches as well, in case the caches, for example, are underutilized, right? And you want to change the hash function on the fly and place your data somewhere else. This is how you would do these steps in the L2 TLB. We first form the index for assuming a page offset of 12 bits. The index here is 2 bits, 0, 0, which corresponds to the first set. We need 2 bits because we have 4 sets in the L2 TLB. We don't find a hit, it's a miss. We have a tag mismatch. And then we form the next index using the 22nd and the 23rd bit to index assuming a 2 megabyte page. And in this scenario, we find out that the index changes. The index points to set 1 for the 2 megabyte one. How do we do this? With an n-step index recalculation again. So what is the pros of this? It's a very simple and practical implementation. Can anyone think of a problem with this? What would be a disadvantage of going one by one through the page sizes to search like sequentially the page sizes in the hardware structure? So the problem is that you have a varying L2 TLB hit latency. So for example, if you have a hit for 4 kilobyte pages, you find your data and you assume it's a 4 kilobyte page and you find it, right? It was the first step because the first assumption you made is that the page is 4 kilobyte. Then you have a very fast hit for the 4 kilobyte scenario. If you hit for 2 megabytes though, you have gone through the step of probing for 4 kilobytes, which makes the process of hitting slower. Also, it's much slower to identify if you have a miss. Like to identify if I have a miss in the L2 TLB, I need to probe all the sizes one by one until none of the sizes correspond to a tag match, basically. Is that clear? Cool. What's an optimization? I can do parallel lookups. I can look up the 4 kilobyte, assuming a 4 kilobyte and 2 megabyte page in parallel. What is the disadvantage of this? That I would need extra circuitry to generate all the indices at the same time and being able to access the TLB at the same time. Also, I can do page size prediction. I can have a learning unit or some sort of perceptron unit that tells me, okay, this is the probing order that you should try that has the highest probability of hitting first, for example. Then we missed also in the L2 TLB, right? Then we need to trigger the page table walker. This is the per core hardware component that walks the multi-level page table to avoid expensive context switches and software handling. And it has basically two components: a state machine, a finite state machine that is designed to be aware of the architecture's page table structure, and registers that keep track of outstanding TLB misses. So in the TLB miss registers, I keep track of which addresses have missed in the TLBs so that I know how to satisfy them. And there's a state machine that generates the addresses basically to access the page table. What is the pros of having a hardware page table? You avoid the context switch in the case of a TLB miss. You overlap the TLB misses with useful computation, and you support concurrent TLB misses. The disadvantage is that you need hardware and area power overheads. You have limited flexibility compared to the software page table walk. And that's how the process looks like. Again, as you mentioned before, you have the page table walk, which accesses the CR3 register. The CR3 register is basically the base of the page table. This maintains the address to the root of the page table. It's called the PML4 level in x86-64 systems. So the page table walk concatenates the contents of CR3 with the first 9 bits of the virtual address to form a pointer. And after you form the pointer here, you access the first level. And using this pointer, you access the next level. Using this pointer, you access the next level. In this way, you access the final level, which basically stores your 4 kilobyte translation. You do 4 steps to access the page table. The hardware, one of the biggest benefits of the hardware page table walker is that it allows overlapping TLB misses with useful computation. So you have a software page table walker, as an example here. You want to load A, this corresponds to virtual page number 1, and you have a TLB miss, right? You're missing the TLBs. So you have a context switch. Why? Because the operating system needs to take over and handle the TLB miss. After the operating system is done, then you need to proceed with load B. And then when you proceed with load B, you find out that you have a TLB hit. This is a completely different load, right? In the case of the hardware page table walker, you load A, you have a VPN of 1, there's a TLB miss, and you do not need to trap to the operating system, which means that you can satisfy quickly the load B's TLB hit. So in parallel with the page table walk happening for load A, you can basically perform the translation for load B. So you do not basically stall load B and the processor, and you save very important cycles, a significant amount of cycles basically, which could improve performance a lot compared to performing it at the software level. So why do we need page walk caches in the page table walker? So the page walk caches, I will not stick a lot to this, they cache basically translations from non-leaf levels of the multi-level page table. They store all the intermediate pointers, as many intermediate pointers as possible to accelerate the page table walks. You basically try to accelerate the whole page table walk process with the page walk caches. And yeah, another big issue with the virtual memory is, when do we do address translation? Do we do it before or after accessing the L1 cache? In other words, is the cache virtually addressed or physically addressed? There is this concept of virtual versus physical caches. And the question is, what are the issues with the virtually addressed cache? Why can I not simply access my cache with virtual addresses? Does anyone have any idea why? Exactly. If two processes have the exact same virtual address, right, and you context switch, you do not know to whom this virtual address belongs to. And this is the synonym problem. No, this is the homonym problem, but the another problem is the synonyms problem. The fact that you have two different virtual addresses which can map to the same physical address. That's another type of problem that can happen in this scenario. So you have the same physical address present in multiple different locations in the caches, which can lead to inconsistency in the data, basically. So the homonym problem is what you said, that you have same virtual addresses that map to two different physical addresses. And if your cache is virtually addressed, then you do not know to whom it belongs, right? And the synonyms happen when you have different virtual addresses that can map to the same physical address. Why can this happen? Because we have different pages which can share the same physical frame within or across processes. The reasons this might happen is because you might use shared libraries, shared data, copy and write pages within the same process. So the question is, do homonyms and synonyms create problems when we have a cache? It depends on whether the cache is virtually or physically addressed. For example, we can have three different ways of accessing or performing address translation. We can first wait until the TLB gives us the final physical address, right? That's the easiest, which means that we have a physical cache. Another way is that we can first perform the cache access using the virtual address and then translate. This is a virtual L1 cache. But this virtual L1 cache, if we do not store any identifier about to whom this virtual address belongs to, then we might face the homonym problem. And another type of access to the cache and the translation subsystem that occurs is the virtual to physical caching, which means at the same time, I will be accessing partially the cache in some way using the virtual address, using some virtual address bits, at least so that I can find the set of the cache, the set that the data belongs to. And I'm going to wait for the translation to be resolved. Why do I do this? I will activate the set for the specific cache line that I need to access. And I will just need to wait until I retrieve from the TLB the rest of the physical address so that I can form the tag. And once I form the tag, I will be able to access the cache. In modern processors, they are able to parallelize this process very effectively. That's why they hide the latency of the TLB hit. Once you hit in the TLB, you can directly access, you supply the physical address, you form the tag, and you perform the tag matching in the corresponding set. So the evolution of the virtual memory subsystem, to get an understanding, some years ago, like let's say 20, 30 years ago, we had a simple address translation subsystem, an L1 data TLB, an L1 instruction TLB, an L1 data cache, and the software page table walker. Why? We had small data sets. There was no need to sacrifice area and power and energy for performing the page table walk processing at the hardware level. In the modern address translation subsystem, we have a lot more components. An L1 data TLB, L1 TLB, a page table walk cache, as we discussed, an L2 TLB, the page table walker, and it's becoming a lot more boosted because we have very large workloads which stress it with very large data sets. As you can see in modern virtual memory designs, such as the iPhone 12 Pro and Intel server processors, we have TLB, L2 TLB size from 1.5 kilo entries up to 3K entries. And different page size design decisions. For example, Apple is using a 16 kilobyte page size, while Intel, AMD, and ARM are using a 4 kilobyte or more pages, basically. So, yeah, should we do one more break? Are you tired, or should I continue? What do you want? Okay, do it. Let's do a 5 minute and then we continue. I got tired. So. So we're gonna now dive deeper into some concepts of research in virtual memory. And as you can understand, there are multiple components in modern computing systems, including the CPUs, GPUs, network interface cards that want to access memory using the virtual memory abstraction, right? So virtual memory is one of the first examples of the most successful integration of hardware and software, and it's becoming a cornerstone of most modern computing systems. But as I tried to tell you through the whole lecture, it doesn't come for free, basically, right? It causes high performance overheads in modern workloads because of two main reasons. We need to allocate data. We also need to translate data. And let's see first some emerging workloads which have popped up. Like we have serverless functions, function as a service, platforms, short input, short output, LLM inference. We have microservices, and all these have the following properties, right? As you can see here, we have a system with 3 different cores, and we interleave different functions and different workloads in short bursts of time. So we're executing, they have a stateless execution, which means that we bring up one of these functions, the function finishes, we don't care about anymore, right? They have very bursty patterns. We might have very high peaks of receiving these sort of functions, and they have very short execution times. What does this problem? What problem does this create? It creates a memory allocation overhead problem. Why? Because these functions spend a lot of time in the operating system to perform memory allocation, handling minor faults, for example, not initialized memory yet, or copy and writes, and less time during their execution, which means that the time we spend in the operating system cannot be amortized because of the short execution of the function. This is an example result which we gathered from a real system. On the y-axis, you can see the fraction of the total execution time as a percentage, and we have many workloads from serverless functions and LLM inference and matrix operations. And as you can see, on average, 32% of execution time, which we measured in a real system, is spent on physical memory allocation, and more specifically on handling minor page faults, simply initializing memory, or satisfying copy and write page faults. On the other hand, we have more traditional, conventional workloads like bioinformatics, graph analytics, database workloads, which have a bit of a different properties. Like they're long running, we might have a database server running for days, weeks, right? They lead to irregular memory accesses. For example, graph analytics is a very sparse type of workload with random inputs, random graphs, which leads to these irregular memory accesses and very large data footprints. For example, some of the graph applications I will show you later utilize more than 100 gigabytes of the physical memory. In this plot, we demonstrate the latency of performing page table walks across many of these graph applications, some quantum simulation workloads. And on the y-axis, we saw the page table walk latency expressed in cycles. So what do we get? What's the key takeaway from this plot? That in modern x86-64 systems, we spend on average 138 cycles to perform a page table walk. Imagine that an access to DRAM might take also 100, 150 cycles. So basically, we double up the access latency to main memory, because we need to first load the page table, perform the page table walk. We spend 138 cycles, and then go and fetch the data from the memory, from the physical location, right? So we almost double the memory access latency. We also have in these workloads very frequent page table walks. So we did an experiment here where we're showing the y-axis the L2 TLB misses per kilo instructions, which means how frequently do we miss in the L2 TLB? And we swept the L2 TLB size from 1.5 kilo entries, which you can find in a baseline processor, up to 64K entries. We almost made it 64 times larger. And what do we observe from this? Even when using the very large 64K entry L2 TLB, we experience a 24 MBKI on average. We miss 24 times every 1,000 instructions in the L2 TLB, which means we need to perform 24 page table walks every 1,000 cycles. So in these traditional workloads, we understand that we have frequent TLB misses, frequent page table walks, and expensive table walks, which cause very high address translation latency that basically hurts the memory access latency of fetching the data. And in these workloads, address translation is rendered as a first-order bottleneck. As you can see here, again, results from a real system. This is the fraction of the total execution time that these workloads, these graph workloads and some quantum simulation workloads are basically spending on address translation. And as you observe, on average, 26% of execution time is spent on address translation. We literally measure this in a real system. And there are also industrial studies which show that modern web, machine learning, and database workloads spend up to 30% of execution time of address translation. For example, this is a graph from a paper called Contiguitas, where the results coming from Meta, and they have shown that web, which, as you can think, corresponds to something like Facebook, expends even almost 20% of its entire cycles on performing address translation. So we have high virtual memory overheads, which are present in both these emerging short-running workloads, as well as in long-running workloads, and for different reasons. Ones are getting hurt by minor page faults. The other ones are getting hurt by address translation. And the virtual memory overheads are also expected to increase as we transition to very large physical address spaces. So we have in the future, we have it basically right now, GPUs and CPUs cooperating with each other using a unified virtual memory, which means that from the GPU memory, from my GPU program can basically access the CPU memory, the GPU program or the CPU program basically are exposed to a very big physical memory. We can directly access storage. We can, from the CPU, we have a byte addressable interface to access a high-end SSD in some cases. We also have memory disaggregation. For example, we can access both local and remote memory modules. And it's much easier right now to connect multiple memory modules to my system rather than making my TLB and the coverage I have much, much larger. And researchers try to save the day and reduce basically these overheads. So we're trying to co-design the hardware and the operating system to reduce the virtual memory overheads. One way to do this is by using a software-managed TLB subsystem. And there are a couple of works which propose such ideas. Let me show you how someone can use a large software-managed L3 TLB to solve some of the problems in modern virtual memory subsystems. So in the MMU, when you have an L2 TLB miss, you do not go to the page table. You go to a mini version of the page table, which is a software L3 TLB that stores directly the virtual to physical translation. And this basically is a bit faster than going to the large page table to performing the page table walk process. So when you miss in the L2 TLB, you access this small data structure first to see if maybe you can find directly the translation there. And this saves you some cycles. The disadvantage is that storing this structure requires operating system support. The operating system needs to find contiguous space in the physical memory, in the physical address space, and it needs to also maintain it, which means if I want to replace an entry in a software L3 TLB, I need software to do it. I cannot do it at the hardware level. Another approach is to leverage virtual address to physical address contiguity to perform very fast offset-based translation, and there are multiple works in this direction. One of them, from ISCA 2015, called Down Memory Mappings, shows that using a virtual address space that uses, for example, these two data structures, right? I'm using one data structure that's 512 megabytes and another one that is 2 gigabytes. If I find a way to place these 512 megabytes, to map them contiguously in the physical address space without putting every 4 kilobyte page distributed somewhere else, then I am able, with a single offset, to find out directly translation of my data. Because using the virtual address, I can subtract the offset or add the offset and find out the location in the physical memory. And I can do this with multiple ranges. If I have a very small number of data structures, then I only need a very small number of these offsets to be able to perform address translation, right? This is a very fast way of performing address translation with the disadvantage of finding the contiguous physical address space. In many modern data centers and workloads and systems, it's very hard to find such a big contiguous free physical memory space. Any questions? Cool. Another approach, some other words say, okay, memory allocation is very expensive, right? Performing the minor page faults or the major ones only at the hardware, only at the software level, it's very expensive. So they have proposed offloading part of the memory allocation at the hardware level. How does this work? How does this work? They delegate part of the memory allocation process to the hardware. The idea is that when the page table worker says the bits in the page table entry are not valid, which means I have a fault. So when we have a fault, we do not trap immediately to the operating system. What we do is, for example, we have a very simplistic approach here, is that we will have a queue with 3 pages if my data, for example, is not yet initialized. So I will allocate my virtual page to one of these 3 physical pages, which are going to be replenished in the background by an operating system thread. So instead of trapping to the OS that performs the memory allocation, gives me a page, I simply make the OS have a daemon that replenishes the 3 pages in the hardware level. So this way, I do not need to stop my application. I just satisfy the fault at the hardware level. And there are many works that propose such type of approaches. Another way is using alternative address mappings, which is very, very close to what your colleague mentioned before about using hashing. I know at least 3 works that try to use hashing, so I'm going to discuss one of them today. I'm going to give a very short overview. It's Utopia. We published it in Micro 2023. The key idea of Utopia is to basically enable both restrictive mappings and flexible mappings to harmoniously coexist in the system. And right now I'm going to explain to you what is a restrictive mapping and what's a flexible mapping. A restrictive mapping is basically the mapping that I use for some specific restrictive segments in physical memory. What does this mean? When I have the virtual page number and the data of this virtual page is stored, for example, somewhere in this segment, then the way I translate is not by using a page table, it's by using a hash function. So I pass my virtual page number through a hash function, and I have direct access to my data without requiring to probe the page table. However, the disadvantage of this approach is that I cannot map my data to any other page in the restrictive segment. Of course, there are different hash functions which allow for mapping it to different places, right? What does this offer? Fast address translation at the cost of limited virtual memory functionalities. Because if I have 2 different virtual page numbers, I cannot make them point to the same physical page, which disables optimizations such as data sharing. On the other hand, we have flexible segments which work the same way that we described before. A virtual page number needs to go through the page table to figure out where it can sit in the physical address space. And using the page table, because we have a dictionary, we can place it wherever we want in the physical address space. So the hash function is basically acts as a very restrictive dictionary. Hash function says you only can put it in some specific locations, while the page table is a very, very flexible dictionary that says put it wherever you want. This way we can support all conventional virtual memory features, while though experiencing much higher latency address translation because we need to access the page table. Another approach is to completely rethink the page table design. Instead of using this sort of multi-level page tables, we can use hash-based page tables with chaining, right? I organize the page table in a hash-based way. What's the problem here? I might have collisions. If I have collisions, then I need to basically create chains. And the problem here is that I will have sequential pointer chasing in case my page table becomes full very quickly. And another disadvantage is that if I want to resize my page table, then I need to rehash all the elements in the page table. Another approach from this work in Sigma-X 2016 is instead of chaining, I will basically try to allocate in the next entry after I face a collision. So the original hash might point here, right? I have a collision, and then I search in the next entry. If I have a collision again and it's taken, I go to the next entry. And I do this process recursively until I find a free spot in the page table. This is called open addressing, basically. And they show that this also leads to better performance than doing chaining. Another approach published in ASPLOS 2020 called elastic cuckoo page tables says, okay, I will organize the page table, I will organize multiple page tables, multiple hash-based page tables, and I will access them in parallel. So this way, I will try to make the page table walk process a lot more parallel. I will basically access with 3 different hash functions, and I hope that I can place into one of these hash tables my data. If I have a collision, I will try to shuffle around so that I can find a new position, a new location for my data. The problem with this one is that it causes multiple parallel accesses to the page table. Another approach is to employ multiple page sizes. And this is an example of what Linux does, what modern Linux operating systems do. They use both 4 kilobyte and 2 megabyte pages. How does this work? THP works by quietly substituting huge pages into a process's address space when those pages are available, and when it appears that the process would benefit from the change. So when you activate transparent huge pages in your system, Linux does the following. If it finds a 2 megabyte page free, it allocates it and says, is this page going to be beneficial for this process or not? It's trying to do this with some utilization features and some metrics that help it decide whether it's going to be beneficial. It also has a background thread called the QH page daemon that is trying to create this contiguity required for allocating huge pages. It tries to find enough contiguous blocks of memory, convert them into a huge page, and transparently allocate them to processes where there is a fit. For example, you shouldn't provide a 2 megabyte page to someone asking for 128 kilobytes because you're underutilizing memory this way. This feature was introduced in Linux in version 2.6 in 2011 by Andrea Arcangeli. And you can see how, for example, your memory layout might look in Linux, right? You might be able to allocate, in some cases, 2 megabyte pages, while some other cases have this sort of white holes that don't help you allocate 2 megabyte pages. This is called external and internal fragment. This is called fragmentation, basically. There are multiple definitions of fragmentation as well. In some cases, data cannot fit, we cannot fit a 2 megabyte page because of these holes, right? But in some other cases, we make space and we can have both 4 kilobytes and 2 megabyte pages in the system. So this is an old book from Mel Gorman on understanding the Linux virtual memory manager. And he explains all the concepts of virtual memory management that occur in the operating system. That's how I learned, basically, how these work. And this is the latest version from Lorenzo Stokes. He's an engineer at Oracle, I think, who launched this book. This is a book that has all the modern approaches to memory management, and it's a very helpful if someone wants to dive very deep into these memory management, transparent huge pages, and all these approaches in operating in the Linux. And this is a very nice talk, which also helped me understand what was the process of dealing with bugs and dealing with design decisions and how they came down to some specific choices when it comes to transparent huge pages. So as you understand, there are a wide range of hardware operating system co-design techniques that aim to improve virtual memory. And effectively evaluating virtual memory techniques is very crucial for the progress of the domain. So we came up with Virtuoso on how to enable fast and accurate virtual memory research with an imitation-based operating system simulation methodology. And we presented this at ASPLOS 2025. It's going to be your lab 6. It's going to be based basically on your lab 6 is going to be based on this work. Let's talk about the challenges in evaluating these sort of designs. The problem, as you have understood already probably, is that we have too many components. We have system components, software components at the operating system level, hardware MMUs, TLBs, page table walkers, and they all interact with each other, right? And this makes the simulation and evaluation of such approaches very hard. An example is the page table and large pages. The page table size depends on the operating system allocation policy. If the operating system decides that it can provide many large pages, then the page table becomes smaller. If the operating system says, oh, fragmentation is very high, I have many holes because of the placement of 4 kilobyte pages, I cannot give you too many 2 megabyte pages. In this case, the page table size starts growing. Another example, you have seen a lot about, have you done the memory interference lecture already? Yes, okay. So you have seen how memory interference works at the DRAM level. So this is a DRAM bank, and application 1 has the page table data stored in this row of the bank, right? And these are page table entries. And application 2 has actual program data in this bank. And in the row buffer, application 2 is currently accessing its data, and the row buffer has activated this specific row. So what happens if application 1 is very translation intensive? What will happen is the following. Application 1 will conflict, will create a conflict with the row buffer contents. It will activate the row that corresponds to the page table entries. And next time the application 2 needs to reaccess the data, because that's a memory intensive application, for example, this will create a conflict again. So the application 2 will face performance penalties because application 1 is translation intensive. So the frequent access to the page table entries in this scenario cause high interference in the main memory, which is an effect that we want to capture when we simulate, when we evaluate our solution, basically. So if we want to evaluate this interplay between components, that's a very critical, because we want to assess the current and new virtual memory techniques. I come up with a new virtual memory technique, and I need to assess all these nuances of the interplay between different components. So researchers have architectural simulators at their disposal. Like, we have two main classes of simulators, simulation-based and full system-based. You have seen in the lecture, in the simulation lecture, some of these: Sniper, Emulator, SAMSIM, Emulator 2.0. We have high simulation speed with a focus on modeling microarchitectural features. For example, SAMSIM models well the caching and the prefetching subsystem. However, it has limited support for operating system primitives. And some of these simulators analytically estimate the virtual memory overheads. What does analytical mean? They use some first-order models. You can think of them as simple mathematical or algorithmic approximations. Like, they might assume that the page table walk latency is 100 cycles, fixed, without any difference, like without any deviation or any distribution, right? Another thing is the minor page fault latency. For example, SAMSIM assumes that the minor page fault latency is strictly 2000 cycles. But as I will show you, this is not true. This is not good enough, basically, because as I will show you in this plot, come results from a real system. The average page table walk latency is not static. It ranges from 33 up to 184 cycles. And we have a very high memory intensity workloads here that face very expensive page table walks. And the lower intensity workloads face a much faster page table walk. So you cannot simply go and fix the page table walk latency, right? Another example, I activate transparent huge pages versus I disable transparent huge pages. When I activate transparent huge pages, the latency of handling memory allocation exhibits very high variability. In the meantime, when the latency of handling memory allocation, when I disable THP, also experiences high variability. So the choice I make with respect to the physical memory allocation algorithm creates variability in my minor page fault latency, which means I cannot set a static number for the minor page fault latency when I want to simulate properly the overheads and accurately the overheads of the virtual memory subsystem. The key takeaway is that these first-order models cannot easily capture the dynamic nature of the virtual memory overheads. And the full system simulators help in that aspect because they enable the execution of the full-blown operating system on top of a hardware simulator. However, if someone has worked with Zen 5, for example, Zen 5 full system, you will see that it has a very low simulation speed, and it's very hard to develop in some cases because you need to co-design both, develop at the same time the operating system and the hardware and the ISA, to make changes in the ISA, which makes the coding effort very high and the development effort very high. So we have these two main classes of simulators. Some of them, like the emulation-based, are very fast much lower speed because of the much lower accuracy because of the analytical models. On the other hand, we have the full system ones, higher accuracy because we capture the operating system and the page table walks and all of these aspects, however, much lower speed. So our goal was to bridge this gap and come up with a simulator for this specific memory management topic, which is both fast and accurately captures the overheads of virtual memory. So we came up with Virtuoso. What's the key idea? We're using a lightweight user space kernel written in a high-level programming language, and we choose the OS modules only related to the desired research. So basically, we're trying to make a mini Linux, let's call it this way, that tries to imitate the full-blown operating system. How do we do that? We take the full-blown kernel that has all of these daemons, processes, services, right? Thread schedulers, managing how to manage NUMA, interrupts, etc. And we strip it away from all these, and we keep only the aspects that we care about during simulation. We care about swapping, transparent huge pages, virtual memory areas, virtual memory object handling, for example. We pack them all together and we construct a lightweight user space kernel, basically, that helps us simulate with much higher accuracy and lower development effort. So we can achieve rapid development and prototyping. We have high simulation speed because we execute only the operating system modules related to our research. And we accurately evaluate it by porting this lightweight user space kernel on top of an architectural simulator. The imitation-based simulation methodology works in the following way. We have the lightweight user space kernel that imitates the memory management that we want, the memory management algorithm that we want, and we have a simulator on the bottom. And how does this work? We have a user space program. We binary instrument it. Binary instrumentation means that you can think of it as some sort of just-in-time compilation where I can figure out the exact assembly instructions being executed on the fly by the program. I take these instructions of the user space kernel instruction stream, I feed them into the performance model of the core that I designed in the underneath simulator. I stream these instructions, and this imitates the operating system level overhead because I was able to simulate the instructions of the user space kernel. At the same time, I also retrieve the functional outcome of the desired policy. For example, do I allocate 4 kilobyte or 2 megabyte page for this specific virtual one, for this specific fault? The lightweight user space kernel can also communicate this information to the simulator. A more detailed example here, we have our workload that generates a memory access. The memory access goes through the performance model. For example, I have the sniper simulator on the bottom. The core model generates the translation request. The translation request goes through the MMU. I have a performance model for the memory management unit where all the TLBs and page table walkers reside. And then it generates a fault. So I do a signal, I send a signal, an actual operating system signal to the user space kernel, which says, okay, I will start running the handler right now. I will handle your fault. I will establish the virtual to physical mapping. It goes through the just-in-time compilation, and it produces a stream of instructions back to the core model of the simulator. So while I'm waiting for this to be resolved, I'm executing the operating system instructions, right, for handling the minor fault. And then when this finishes, I will accumulate it in the total translation latency because I need to take into account right now the fault latency plus the translation latency. When it finishes all this accounting, right, this performance accounting, it needs to send the page fault outcome. In the TLBs, am I going to store a 2 megabyte translation or a 4 kilobyte translation or a 16 kilobyte translation? So we basically built Mimic OS, which encapsulates many modules of the operating system, like the body allocator, radix-based multi-level page table, and many more. There are more details in the paper about that. And we create a full tool set, which encompasses multiple hardware, software co-designed components of multiple state-of-the-art virtual memory techniques, different page table designs, memory tagging, contiguity schemes, and much more. As you're going to find this probably some of them in your homework. It's not going to be something very tough and advanced. But yeah, you can find all these also if you want. This sort of toolset basically enables researchers to evaluate and prototype current and brand new virtual memory techniques. It's a highly versatile simulation framework. We integrated with 5 different simulators, including Ramulator and MQSim, and we validated it against a real system. We basically ported it on top of Sniper and validated it against a Linux kernel running on the high-end server-grade CPU. Where we found out that when we run the simulator alone, Sniper, which doesn't capture the virtual memory overheads accurately, when we integrated Virtuoso on top of it, we improved the IPC modeling accuracy by 21%. And compared to the full-blown Gem 5 full system simulator, which simulates the actual operating system, we are within 9% of accuracy. And when it comes to capturing the page fault model, if we integrate Virtuoso with Sniper, we can model the page fault handling latency with 66% accuracy within 15% of Gem 5 full system. When it comes to speed, in the y-axis, we show the slowdown of porting Virtuoso on top of existing simulators. And as we show that porting MimicOS on top of these simulators causes on average a 20% overhead, while enabling the full system mode, the full-blown OS system mode on Gem 5 causes 77% overhead. And we showcase Virtuoso's versatility by evaluating multiple different use cases, which you can find in the paper. I will describe only 2 of them. First, how we evaluated different page table designs, and how we evaluated different physical memory allocation policies. So diving into the page table designs first, we evaluated the Radix. Radix is a multi-level 4-level page table that the baseline is using. An elastic cuckoo hash-based page table, the one that performs multiple memory accesses. And we sweep the fragmentation. Why did we sweep the fragmentation? Because we wanted to sweep the number of available 2 megabyte pages in the system. And we used workloads from these suites. So as you can see in the y-axis, the reduction in the total page table walk latency over the baseline page table design. And as you can see, as we decrease memory fragmentation, which means more and more 2 megabyte pages are being given to the application, the page table walk latency reduction of elastic cuckoo hashing, which means accessing the hash-based page table with more 2 megabyte pages, leads to a much higher latency reduction compared to what we gain by providing 2 megabyte pages to the baseline design. But at the cost of what? At the cost of a much higher amount of DRAM row buffer conflicts. Even though elastic cuckoo hashing reduces the page table walk latency, it increases the amount of conflicts caused in DRAM. Why? Because it performs multiple accesses per page table walk. So the second use case is about evaluating physical memory allocation policies. Our evaluation methodology is the following here. We have the baseline allocator with a buddy system, and we have Utopia. In Utopia, we have part of the memory organized with hash-based mapping. This is the restrictive segment I talked before. And as workloads, we have the short input, short output LLM inference, for example. So we use Mistral, Llama, and Bagel in this context. What do we observe in this? What do we show in this plot? On the y-axis, you can see the physical memory allocation speed up. How much do we speed up physical memory allocation, minor page faults? If we restrict the mapping, we can basically, using a single hash function, without any sort of auxiliary data structure, find out directly where to place our page, right? And this way we accelerate physical memory allocation by 2.17x in these workloads. There are a lot more details and use cases in the paper. Virtuoso is open source. You can find it on GitHub. We have a website for the documentation. We also organized a workshop and tutorial, the Micro 2025. You can find the link here. And we hope that it establishes a common ground for virtual memory research. I hope you have fun doing, whoever does the bonus lab. And in summary, virtual memory gives the illusion of an infinite capacity. We have a subset of virtual pages which are located in physical memory. Again, the page table manages the virtual page to physical page mapping. This is how we do address translation. The MMU, the TLBs speed up the address translation process. The multi-level page tables keep the page table size in check, and using different page tables for different programs provides memory protection with the access control bits and with all the things that we discussed. There is a lot more, which of course we cannot cover into one lecture. It's about how virtual machines handle translation. It's about how hypervisors handle memory allocation. For example, in virtualized environments where you have virtual machines, right? The virtual machine has its own virtual address space. And there's an additional level of translation because you have a guest operating system with a guest, with its application having a guest virtual address, have a host operating system. Host operating system is using host virtual addresses that get mapped at the end of the day to the, at the end of the line, basically to the main memory. So you need to go through two levels of translation to translate in virtual machines, which makes the address translation process a lot more expensive compared to systems with native execution. One of the groups works on address translation, how to completely rethink address translation to perform much faster both allocation and translation is called VBI, the Virtual Block Interface. I suggest you read it. It's a very cool work. And it's also in your required readings. And another work which I also focused some years ago is, we published it in Micro 2023. It's about how we can basically improve the baseline system and leverage the underutilized cache resources to store, to pack a lot of TLB entries. So we are basically providing a way to pack many TLB entries inside the underutilized resources of the caches. And the caches are much bigger than TLBs, which gives you a lot more speed and reach, translation reach, which is the memory coverage, basically. So some parting thoughts. Virtual memory is one of the most successful examples of architectural support for programmers. How to partition work between hardware and software hardware-software cooperation. It poses this programmer-architect trade-off. And going forward, there are many aspects to it that need to be thought about, like how do we handle increasing huge physical memory sizes when we have multiple memory nodes, distributed systems, when we have a hybrid physical memory system, which means we have a DRAM, we have a non-volatile memory, a hard disk, an SSD, many accelerators in the systems, like we have a GPU, a TPU, an NPU, that try to address the same physical memory or a distributed physical memory. And how do we handle allocation, translation, and many more in virtualized systems? So that's what Onur said in some lecture. And what we learned today is that it's also the virtual memory, stupid. There are more lectures from the group on virtual memory. And I think this one is also a nice one from Onur back in CMU. I think it was, I think you covered a lot of stuff there that I was not able to cover. So I suggest that people watch it if you want to go into even more deeper details. Yeah, and basically you can check also the last cutting edge research where I present in detail victim as well, which I didn't present today. It's in fall 2024, the lecture 25. I think you will understand how also caches interact with the TLB subsystem. And also we have many research opportunities in this direction and other directions. You can email Mohammed and Professor Mutlu with your interest. And there are many, many projects. Something happened there. I didn't have any more slides, but I was away from the computer, so. Yeah, so we have basically multiple research opportunities. You can talk to me or Muhammad, Onur, please email them. And there are many diverse topics that you can work around, from bioinformatics to processing in memory, RowHammer, and much more. Yes, I didn't have any other slide, literally, so it was my final slide, this one. Thanks a lot for paying attention today. I hope it was a nice lecture. Any questions? Nice. I am waiting for your lab submissions if you do them.